After many days of dealing with COVID, practices like wearing a mask and social distancing have become super common. But why is it that professionals ask us to do these things? Hi, my name is Lasya, and today I'm going to be talking about the math behind modeling epidemics.
Epidemiologists use something known as the SIR model to model epidemics. Now, when you hear the SIR, you might think of the word you used to call someone else, but it's actually an acronym of the three groups found in the model. The first one is the susceptible group, the second one is the infected group, and the third one is the recovered group. Along with this, we're going to be using some variables to help further our understanding, and we're going to be using the Greek letters beta and gamma to do so. Now, what are these variables used for? These variables allow us to understand the shifts between each of these groups, but their specific meanings? Beta is the transmission rate of a disease, or how easy it is for a susceptible individual to become infected. Gamma, on the other hand, is the recovery rate of a disease, or how easy it is for an infected individual to recover. Along with these variables, we're going to be doing some calculus, but don't worry, we're just going to be sticking to the basics. A derivative is the instantaneous rate of change. And now you might be wondering, well, what does that mean? Think about it this way. You're looking at a large data set of COVID infections, but you just want to know how many people got infected on Monday. Well, Monday would be your instance, and your change would be from susceptible to infected. Derivatives are represented in a dx/dt form where x is the variable and t is time. You can actually replace x with variables like si and r and get some rates and derivatives that we'll be using later on. ds/dt is the rate of change of susceptible individuals, or the amount of people leaving S. didt is the rate of change of infected individuals, or the amount of people entering I and leaving S and leaving I. And drdt is the rate of change of recovered individuals, or the amount of people entering R and leaving I. Now, as you can see, we have some holes in our chart, and we're going to fill in those holes with equations that show how people move from one group to the other. dsdt is represented by negative beta si, and the negative shows the people leaving S, and therefore entering I, which is why for didt, it's positive beta si minus gamma I, where the negative shows the people leaving I. And drdt is positive gamma I for those who are entering R. Now we have a cohesive chart of showing how people move between each of these groups. Let's move on to a physical model. Now we're going to have a physical model with cups for the groups and models for people. The infected and susceptible cups have holes under them, and in the first demonstration, the beta IS hole underneath the S cup is actually smaller. As you can see, because of the smaller hole, not many marbles went through and not many people got infected. This means that there's a low transmission rate, which is representative of people wearing masks and socially distancing. However, in the second one, a lot more people got infected and it takes longer for them to recover. This is because there's a larger beta IS hole and a larger transmission rate, meaning that they didn't follow those safe practices. Now, when someone asks you why you're wearing your mask, you can flex your newfound knowledge on them